Okay, in application 3, we will focus on system identification of the second order approximation. Okay, so in the first place, we need to look at the theoretical background. Like the mass spring damping system. The mass spring damping system contains the mass, the preserving energy, C, damper coefficient or the loss energy, and K is the storage energy or the spring factor. And so you can model anything by using the mass spring damper analogy in the real life or theoretical background. Okay, and so the mass spring damper system is a classical mechanical model describing the second order and may or many physical systems, like to the what its dynamic can be given with what the mx dot dot plus cx dot plus kx is equals to the what to the f. Okay, and here the xt is equals to the what the displacement, and the m is the mass, and c is the damper, and k is the what the spring. Okay, so these are the system, these are the dynamic, but in the differential form of the second order equations. Okay, and so in the second place we need to continue with the what the Laplace transform and transfer function. Okay, we need to use the Laplace transformation and the transfer function to be built in this system, because we need to give the what every differential operator into the algebraic one. Okay, and so the taking Laplace transformation gives us to the what to the xs, we have the double dot in here, ms square plus c contains the 1 dot s, and plus k is equals to the what to the fs. And so the r transfer function based on the what for a given fs to the xs, and so 1 divided by ms square plus cs plus k. Okay, these are the general notation about what the second order system differentiation, because the s is in the form of what over 2. Okay, and so we know also a standard form of second order system. Okay, but how we can define the standard form of second order system? Just remember that we have two important parameters: natural frequency and the damping ratio, which means that the zeta values, right? And so we can write the following formulation: the GS or any GS can be represented with what? The Wn square divided by S square to zeta Ws plus Wn square. And so any second order system can be modeled based on what? The natural frequency and damping ratio, because everything contains these functions, these constants in real life or in physics or in universe. Okay, so we have two equations in here, and so we need to equalize these terms. Equalizing equations at characteristic 1 gives us 2 what? S square plus 2 zeta omega n s plus Wn square is equal to 0. This is the general form of characteristic equation. And also we have the S square C divided by ms plus K divided by m is equals to the 0, right? This is the what? The first equation, mass spring damper equation with the division rate of the what? 1 divided by m. And so this easily equals to the what? R nominations. And so these values is equals to this one, these values is equals to this one, okay? And we can write these values just like this one. The omega n square is equals to what? K divided by m. Or 2 zeta omega n is equals to the what? The C divided by m, okay? These are general parameterization for about the what? Identification of the second order system. And 1.4, the time response parameter. Should be discussed about the what in terms of the second order parameters. And so we have 4 important equations to model to the what? To model the coefficients of the what? The MCK in here. First of all, we need to write the peak time formulation. For every second order system, we have these conditions. The peak time can be described with what? The pi divided by Wn times 1 minus zeta square. Okay? This is the peak time formulation. And also we have the percentage overshoot values. The function PO is equals to what? The exponential over minus zeta times pi divided by 1 minus zeta square. Okay? And also this is the percentage rate, and so we need to multiply with the what? With the 100%. Okay? This is the second formulas. And also we have the rise time. This is another important parameters. TR can be approximated with the what? With the values of the what? The pi minus theta value, Wn minus zeta square. Okay? The TR is given in these forms. And so the theta is equals to what? The arc cos zeta value. Just remember that. And also we have another parameters in here. It's the settling time, guys. The settling time, Ts, settling time is equals to the what? The 4 divided by zeta times Wn. 4 to what? 2% error at the steady state values and the final steady state values. Okay? So, how we can solve these equations in these forms? First of all, we need to create another section estimating zeta and Wn. if we estimate these two things, and so we can model, we can write our formulations in the what, in the second order form on the what, transfer function domain. Okay, and so from the percentage overshoot from graph, the graph may have this kind of response. For example, this is the measured data XD, and so the R measured data is just like this one, for example. And so the maximum overshoot is defined with what, with this value PO. Okay, and so also we can assign this is the peak time, right? We can find these values from the graph, and so the zeta value is calculated with the what, minus ln PO divided by 100, and so the square root pi square plus ln PO divided by 100 square. Okay, this is our formulation of the what, the zeta. And so if the graph gives us the percentage overshoot with respect to the what, steady state values, and so we put it into the what, into this equation, and so we can find easily the zeta values. Okay, and after that, from the peak time, we can write the Wn is equals to the what, the pi divided by t peak times 1 minus zeta square, because zeta is have been found at the previous step. Okay, so if we have these two data, and then 1.6 calculating the C and K values for a known mass. Mass is easy to calculate this finding, right? And so for a known mass, we can write the K is equals to what, the M times Wn square, is the first formula, and the C is equals to what, 2 dot M dot zeta dot Wn. Okay, this is the basic formula for a what, for a given mass, because it's a mass can easily be calculated from the what, mechanical parameters. Okay, so in the next lesson we will build to the what, to our MATLAB example for the second order approximation of this system.